Continuing on with Year 13 binomial expansions. In the last video we looked at how to expand 1 plus bx to the power n, where n wasn't necessarily a positive integer anymore. And we found that this is approximated by 1 plus nbx plus n times n minus 1 over 2 factorial bx squared plus, and the pattern continues. The next term would be n times n minus 1 times n minus 2 over 3 factorial times bx all cubed, etc. And this expansion was only valid if the modulus of bx was less than 1. That is, if minus 1 was less than bx was less than 1. Otherwise, this series would blow up to infinity as the terms got bigger. Well, what we're going to look at in today's video is how we deal with this situation. Notice here it was a 1, now it is not. So all we're going to do is we're going to force it to be a 1, and then we're going to apply exactly the same theory that's written above. So in this case, we've got an a, so I'm going to write the inside of the bracket here as a into 1 plus b over ax about n. So all I've done is I've pulled an a out, and once you get fairly fluent with this, then you can just kind of crack on and not have to do this line. But I do recommend doing this line because it's not just pulling an a out, you're actually pulling an a to the n out. The most common mistake made by students in these questions is that they don't raise it to the power n. But this step kind of illustrates why that is true. So now I've got a product of two things in the outer bracket, and I'm going to raise that to a single power, so I can apply that power to each of those two things separately. So that is a to the n into 1 plus b over ax to the n. And the idea is that now I just apply the binomial expansion theory to this, because that is of the form 1 plus something times x to the power n. Okay, just the something is now b on a rather than just b. Okay, so that's the general theory. Once you've got your answer to the expansion, just times all the terms by a to the n, and there you go. So, 2 examples, and then I have a third one which I'm going to give you 2 methods on how to do, and then I'm going to leave you to do it, and I'll give you the answers at the beginning of the next video. So example number 1, we're going to expand 4 plus x all rooted up to and including the cubic term. So notice that this is not a 1, but in the formula book you are told that 1 plus, I'm going to put this at capital X again, to the power n can be approximated as 1 plus nx plus n times n minus 1 on 2 factorial x squared, etc. So this is only valid if the number inside the bracket is the number 1. This is not the case, we've got the number 4, so I'm going to pull the number 4 out. I'm going to say that this is equal to the square root of 4 into 1 plus x on 4. So if we were to multiply out that bracket, I would get back to the original question. Okay, 4 times 1 gives you the 4, and 4 times x on 4 gives you the x. So that is just root 4 times, I'm going to write this now as 1 plus x on 4 to the power of a half. So root 4 is just the number 2. 1 plus x on 4 to the half. So that's the same thing as this question, except now we've got it into the form of 1 plus something to the power of n, so we can apply our binomial expansion theory. Okay, so I'm just going to bring the 2 out and just leave it there. I'll come back to that later. I'm going to apply this. In this case, we've got n is going to be a half, and capital X is going to be our x on 4. So the first term is always the number 1. Get the number 1 in there. Then we've got nx, so it's going to be a half times x on 4, so that is just x on 8. Plus n times n minus 1, so that's a half times minus a half divided by 2 factorial times x squared, but x is x on 4. And in the next term, because it wants the cubic term as well, you need to continue the pattern from here. So it's going to be n times n minus 1 times n minus 2 divided by 3 factorial times x over 4, or capital X, cubed. And that would continue infinitely, but we're stopping at the cubic term. Okay, so now we're going to simplify all the terms. So again, just leave the 2 where it is. We've already simplified the x on 8. Now we've got this thing to deal with. So I recommend again again, getting a calculator out for this. So we're going to have a half times minus a half times, divided by 2 factorial, which is 2, times 4 squared, which is 16. Okay, that's now in the denominator this time. So that is going to be minus 1 over 128. So minus x squared over 128. And then I can modify this top one here. That's now going to be 4 cubed. That's 3 factorial, so that's 6. And I also need to times the top by an extra term, which is n minus 2. And that gives me 1024th. So I get plus x cubed on 1024. Dot, dot, dot. So up to the cubic term then, I can now bring the 2 in. So I can say that the square root of 4 plus x is approximately 2 plus x on 4 minus x squared on 64 plus x cubed on 512. And this expansion is valid for the x on 4 as being less than 1. So the modulus of x on 4 is less than 1. So that means the modulus of x is less than 4 if I times that by 4. In other words, this expansion is valid between minus 4 and 4. There we go. Okay, example number 2. A little bit trickier. I did change my mind. It was going to be the cubic term, but that was too cumbersome, so I changed it to the quadratic term. But here we've got a quotient, we've got a division here. So what I'm going to do is just going to apply the binomial expansion to both of these terms separately. So we've got 1 plus x to the power of a half, and we've also got 2 minus x to the power of minus 3 on 2. Okay, so this surd is these two bits multiplied together. I beg you to see that that is indeed correct. So we can apply the binomial theorem to that. So it's 1 plus nx plus n times n minus 1, which is minus a quarter, divided by 2 factorial, which is minus an eighth, times x squared. So it's going to be minus x squared on 8. And the next term is going to be half times minus a half times minus 3 halves, which is positive 3/8. Divide that by 6 for the 3 factorial. It gives me 16th. X cubed on 16. Okay, so that's that expansion. I only wanted the quadratic term, so I don't need that. I don't even need that one. Okay, up to the quadratic term. Now, this one doesn't have a 1 at the beginning, so I can't just jump into the formula. I've got to pull that out first. So I'm going to say this is equal to 2 to the minus 3 on 2 into 1 minus x on 2 to the minus 3 on 2. Okay, and once you get proficient, you can just jump straight from that to that. We can see that this term is now out as a multiplier, and we can apply the binomial expansion to the rest. So that is approximately equal to 2 to the minus 3 on 2. I'm going to write that as a nice surd as opposed to a not nice fractional power. That is root 2 on 4. Into 1 plus nx. Now n in this case is minus 3 on 2, and the capital X is minus x on 2. Don't forget to take the negative with you. Okay, the negative is part of the capital X. Okay, so this term is going to be n, which is minus 3 on 2, divided by 1 factorial, and that is going to be times by x squared. So the coefficient will be the minus a half. That's not squared, it's 1. So that gives me 3/4. So I get plus 3x on 4. And then the quadratic term, very similar, except I need to times the top by an extra n minus 1. So that's times minus 2.5. The bottom is now divided by 2 factorial, and this is now squared. And that gives me plus 15x squared on 32. And again, I could continue, but I only want the quadratic term, so I'm going to stop there. And now I can bring in this. What I'm going to do instead is I'm just going to say that this is actually equal to the product of those two. So the answer to the question is going to be equal to root 2 on 4 times 1 plus 3x over 4 plus 15x squared over 32, and then times by this expansion, which is 1 plus x on 2 minus x squared on 8, okay, and so on. And then I'm going to expand this bracket here to give me my final answer. So 1 times root 2 on 4 is just root 2 on 4. The linear term, I'm going to get 3/4 plus a half, which is 5/4, and then 5/4 times that is going to be 5/16 root 2. So that's plus 5 root 2 on 16x. And then finally the quadratic term, just be careful here because I've got a quadratic times a linear times a linear, and a constant times a quadratic. So all three of those will give a quadratic term. So I'm going to get minus an eighth. So minus an eighth, 0.125. I'm going to get 3/4 times a half, so that's 3/8, so plus 3/8. And I'm also going to get 15/32 times 1, so that's plus 15 over 32, which gives me 23 on 32, and then divide that by 4 to give me that, which is 23 on 128, so plus 23 root 2 on 128 x squared, and that is up as far as the quadratic term. That's the answer. Okay, on to my final example, which I'm not actually going to provide for you. I'm just going to get you started on it. There's two different ways you can do this, and sometimes a question might lead you through one of the two ways, in which case just follow what the question says. But if a question just says to expand this up to as far as, in this case, a quadratic term, then you can use either method. It doesn't actually matter. So method 1, consider that this is equal to 8x plus 4 multiplied by 1 minus x to the minus 1 multiplied by 2 plus x to the minus 1. And what you'll do is you'll expand that binomially and expand that binomially, which actually reminds me, again, I forgot to give the restriction on x here. The restriction on the top expansion was the modulus of x is less than 1. The restriction on this expansion was the modulus of x on 2 is less than 1, which is the modulus of x is less than 2. But for this expansion to hold, the actual final answer, both of these must hold. This one only holds between minus 2 and 2. This one only holds between minus 1 and 1. So you need to take the more restrictive range. So this expansion is actually only valid for a modulus of x is less than 1. Because, for example, if x was 1.5, this one, yes, would be satisfied, but this one wouldn't be, therefore is not valid. They both have to be valid for the product to be valid. So you take the more restrictive range. So we expand those two, and again, you take the more restrictive range, which is what reminded me. So in this case, actually, the restriction on this one is going to be modulus of x is less than 2, and this one, modulus of x is less than 1. So the restriction will be the modulus of x is less than 1 again, and that's because that's the more restrictive one. Okay, so that's method 1. Method 2. Which a question might guide you through is we use partial fractions on this first. So we would say 8x plus 4 divided by 1 minus x into 2 plus x is identical to something over 1 minus x plus something else over 2 plus x. Apply your partial fraction theory, which I have some videos on already, so check back at those. Essentially 8x plus 4 is identical to a into 2 plus x plus b into 1 minus x, and I prefer the method of equating the coefficients. So 8 is going to be equal to a minus b, that's the coefficient of x, and the constant is going to be 2a plus b. If I add those together, I'm going to get 3a equals 12, so that's going to give me a must be 4. And plug it back into the top one. If a is 4, b must be minus 4. Check with the bottom one. 2 times 4 is 8, minus 4 is 4. Good. Okay, so there's my binomial coefficient. partial fraction numerators. So I can, instead of expanding this binomially, I just expand 4 into 1 minus x to the minus 1 minus 4 into 2 plus x to the minus 1, and I can expand that instead. Okay, pros and cons to both. Method 1, you don't have to faff around with your partial fractions, but you do have to do a product at the end. Method 2, yes, you've got a bit of faff with the partial fractions, but there's no product at the end. You just add the two together. Makes the final step a little bit easier. I don't think there's any particular advantage to either of those methods. They both are good, both have potential pinch points. But if a question does lead you through one of the methods, then I suggest you just follow what the question says. For example, a scaffolded question might have this as part A, and then expand that as part B, in which case it makes sense to continue with this, rather than go back and do this, although you would still get full credit if you did do that. Right, yeah, one more video coming on binomial expansions, which is going to look at problems, and I'll give the actual answer to this one in that video, so check that one out. Thanks for watching.